Welcome to our video on probability. In this lesson, we'll learn about classical probability theory and explore several concrete examples to build our intuition. Let's start with the definition of classical or theoretical probability. If all outcomes of an experiment are equally likely, the probability of an event A is defined as the number of outcomes in event A divided by the total number of possible outcomes. This ratio always results in a value between 0 and 1, inclusive. Let's explore our first example, flipping a fair coin. When we flip a fair coin, there are two possible outcomes, heads or tails. We'll denote heads as H and tails as T. This gives us a sample space of omega equals the set containing heads and tails, which has a size of 2. If we define event A as getting heads, then A equals the set containing just heads. So the probability of getting heads is the size of event A, which is 1, divided by the size of the sample space, which is 2. This gives us 1/2, or 0.5, which matches our intuitive understanding that a fair coin has a 50% chance of landing on heads. For our second example, let's consider rolling a fair 6-sided die. When we roll a die, we have 6 possible outcomes, 1, 2, 3, 4, 5, and 6. Our sample space omega contains all these numbers, giving us a total of 6 possible outcomes. If we define event B as rolling a 4 or a 5, then B equals the set containing 4 and 5. Let's highlight our event on the die diagram. The probability of event B is the size of B, which is 2, divided by the size of the sample space, which is 6. This simplifies to 1/3, or approximately 0.333. For our third example, let's examine drawing a card from a standard deck. A standard deck contains 52 cards, with 13 cards in each of the 4 suits: hearts, diamonds, clubs, and spades. Our sample space consists of all 52 cards in the deck. Let's define event C as drawing an ace. There are 4 aces in the deck, 1 in each suit. The probability of drawing an ace is the number of aces, which is 4, divided by the total number of cards, which is 52. This simplifies to 1/13, or approximately 0.0769. Now, let's examine a more complex example, finding the probability of drawing at least 1 ace when drawing 2 cards without replacement from a standard deck. We'll approach this using the complement rule of probability. First, we'll find the probability of drawing no aces, and then subtract from 1 to get our answer. For the first draw, the probability of not getting an ace is 48 out of 52, since there are 48 non-ace cards in the deck. For the second draw, there are now 51 cards left in the deck. If the first card was not an ace, there are still 47 non-ace cards remaining. So the probability of not getting an ace on the second draw is 47 out of 51. By the multiplication rule, the probability of getting no aces in both draws is the product of these individual probabilities. This gives us 48 by 47, divided by 52 by 51, which is 2,256 divided by 2652, or approximately 0.8521. Therefore, the probability of getting at least 1 ace is 1 minus 0.8521, which equals 0.1479, or about 14.8%. Let's conclude by reviewing some key properties of probability. The probability of an impossible event, represented by the empty set, is always 0, and the probability of a certain event, represented by the entire sample space omega, is always 1. If events A and B are disjoint, meaning they have no outcomes in common, then the probability of either A or B occurring is the sum of their individual probabilities. For any event A, the probability of a not occurring, denoted as A bar, is 1 minus the probability of A occurring. We can visualize these properties using Venn diagrams, which help us understand the relationships between events in a sample space. In summary, probability gives us a mathematical framework for quantifying uncertainty and analyzing random events. We've covered the definition of classical probability, examined simple examples with coins, dice, and cards, explored a compound event involving multiple draws, and reviewed the fundamental properties of probability. These concepts form the foundation for more advanced topics in probability and statistics, with applications in fields ranging from science and engineering to finance and data analysis.